1, 0.
1, 2, 3, 4.
Hi everyone, today we're going to look at part 2 of transformations 2.4, 2.5. Last class we took a look at some transformations in which we expanded, compressed horizontally, vertically, and we did some translations left, right, up, and down. We touched on reflections a little bit. We're going to add on that right now, and then we're going to look at a third type of reflection that you haven't seen before. So we know from y equals f of x, if you have something in which you have y equals negative f of x, if the negative is in front of your function, and you remember this from, say, you pick the function of a parabola in the past, you would have a parabola that opens up. If you put the negative right here, then you know that you reflected over the x-axis and it went upside down. So we're going to say that that's our reflection over the x-axis, and we'll talk about this a little bit more, but that's when the point xy becomes a point x comma negative y. Okay, if your x becomes a negative x right here, okay, this means it's affecting the x values, which were our horizontal values. So your horizontal values would then say it's going to flip something on its side rather than over top of each other, and that's going to be a reflection over the y-axis. And then finally, third type of reflection right here, this is brand new. This is our inverse. And our inverse is when you switch x and y with each other. So if you have the point xy, it now becomes the point yx, and that's going to produce a reflection in the line y equals x. When you write it, it's going to be denoted like this, and that's not saying f to the power of -1. That is your symbol for saying we're taking its inverse. So if you want to take a look at why that's the case, if we pick a random point, so in this case here we have the point 2,5, and we're going to say what happens when you have a negative in front of your function. Well, when we have a negative in front of our function, we know that that means that the point 2,5 is now going to flip upside down. Okay, so our y value, our function, is becoming negative. So the point 2,5 now becomes a point 2, -5. Okay, and that value there, it's flipped over the x-axis, and that's why we have our x-axis reflection. So that differs from if we have f of x and it becomes f of -x. So here our 0.25, our x value is now being replaced by a negative x. So that means that 2 is now -2. So our 0.25 right here now becomes the point -2, 5, and this would be reflecting over the y-axis. So if you take a look at the point here for our inverse function, our third example, by definition, when you have the inverse, we switch x and y. So our 0.25 becomes the 0.52, and if we draw the line y equals x in right here, you'll notice that we're reflecting over the line y equals x. So to expand beyond a point, we can take a look at this on a couple of different graphs. Right here we have a negative in front of our function, so right away I would label that. Now, if that's in front of the function, that's just like what we did with parabolas, opening up and opening down. So this is going to be our reflection over the x-axis. We take a couple of our points, and whatever values you have, you're going to mirror them over the x-axis. So this point at 0, 3 right here goes down to 0, -3. This point at 2, -3 becomes up here, and you create a brand new function that looks like a mirror image over the x-axis. Now, inverse functions are a little bit tricky to graph, and sometimes they can get a little bit overwhelming. So let's highlight our key points again. And I'll try and give you a couple tips as we go along the way with this. So I guess the first thing I would say is your x-intercepts, when you take the inverse of that, they're going to become y-intercepts. So you're going to have a y-intercept now at -1, +1, and +3. And then we have our maximum point and our minimum point. So we have a point at 0, 3. So that's going to become point 3, 0. And then our point 2, -3 is going to become -3, 2 right here. Okay. And then if you want to figure out the best way to be able to join them, think about this. If our first point right here is at -1, 0, that's right here for its inverse point, and it went from there up to 0, -3. And if that becomes 3, 0 right here, then what we could do is we know it's going to look like that. So we just go in the order of what you had with your original function, and that is now going to be your inverse. And that is actually not a function because it would fail the vertical line test, but that is the inverse of the original function. Okay, so algebraically, we want to take a look at what happens when we take the inverse of something. We have a couple notes right there. I'll let you read through them. And what we want to be able to do is when you solve for the inverse algebraically, essentially we're just switching x and y with each other and then resolving for y. So here we could say we have x equals the square root of y plus 1, and we want to resolve for y. So let's square both sides to get rid of that square root, and x will equal y plus 1. X squared equals y plus 1. We want to isolate for y, so let's subtract 1 over. And then now we have successfully done that. So let's denote that. If we're saying what its inverse is, we're going to say it's something like the inverse is going to be equal to x squared minus 1. Now, I just want to add one more point to it, and this point's a little bit strange. So if you take a look here, it says we want to keep this a function. And right now, with this is defined if you're to talk about the domain and you're to talk about the range right here. So if you're to graph this, it would look something like this. Okay, and so what we want to be able to say with that is, yes, that's true, but x had to be a value that was greater than -1, and I guess you could also say then that y was a value that was greater than 0. And so when we take a look at this and we want to be able to place a restriction on the example that we have right here, you could say, well, that's true, but it's only true if this was when y is greater than or equal to 0. This is true when what would be the inverse of y is greater than or equal to 0? It would be if x is greater than or equal to 0. And that just makes sure that our inverse is still a function. Because if you're to, would be the exact same as the original. If you're to look at the original and you have something like that, and you're to graph x squared minus 1, well, right now, x squared minus 1 would look like a parabola, and that's not the same as this. So by putting this restriction on, we've been able to say, now that is exactly the same. So this part right here is definitely something that's going to be a little bit tricky, and you'll want to look over that a little bit more. Okay, now one of the most common examples that you see in pre-calc 12 books is you have something in which you have a rational function. You got an x on the top, you have an x on the bottom, and you want to find its inverse. So we switch x and y, and we want to isolate for y. We can play around with this for a little bit, and I encourage you to pause this right now and try to do that. And if we do that, and we get x, y minus 8 equals 2y, and we want to solve for y, your best way to solve for y when you have two different y values, you have your xy and you have your 2y, are to get your y's onto the same side and then factor out a y. Okay, I can't stress that enough. So get your y's together and then factor out a y. So I'm going to subtract 2x or 2y over here and then add 8x onto the other side just to keep my values a little more positive. When you do that, you get xy minus 2y equals 8x. Now I can't join xy minus 2y, but I could factor out a y. So now if I want to isolate for y, I just divide by x minus 2, and I have successfully gotten my inverse. Okay, if you want to know what the restrictions are for the inverse function, take a look right here. Do you have a non-permissible value? Do you have something which you could create a 0 on the bottom? And you do when x is 2. So that would be your non-permissible value. Okay, and this final example here for some of the odd inverse algebra that you're going to have is, it says, it's not asking you to solve for anything, it's just saying determine the restrictions when you have f of x equals x minus 3 squared plus 4, so that its inverse would be a function. So imagine you have something like this. Let's graph our parabola at 3, 4. So here's a sketch right here, 3, 4. And we have a parabola that would look like this. Now if you were to take the inverse of that shape, you're going to create something in which the vertex of 3, 4 is now going to be 4, 3. And you're going to create, if it used to open up like a U, it's going to end up looking like a C. So you remember from pre-calc 11, you learned about something called the axis of symmetry. And the axis of symmetry splits our functions down the middle. And if you look at half of that function right here, then that right there, if you were to take just that part and take the inverse of that, that would produce this top half here. And that would still be a function. But when you have that full C shape, that's not a function. So what we could say is, if you restrict this right here so that you're saying this, when x is greater than or equal to 3, I'll produce something that will be a function for its inverse. And you can actually say there's actually two answers, because I could have also said that would also be true if x was less than or equal to 3. Both of those work. I think if you said just even less than 3, that's also good because you've already talked about 3 working. But I think that your teacher would probably be pretty generous on how you notate that. Okay, so the key for a question like that is look for the axis of symmetry, whatever splits the vertex, and that's going to help you produce your solution. Okay, common type of question is going back to what we did in 2.3. We have f of the inverse of g of x. Okay, so here's an f of x function, here's a g of x function, and they want us to now do something that involves the inverse. So before you get started on a question like this, and I think you'll see a couple of those in the homework, you want to find the inverse of g of x to begin with. So let's not even worry about the question yet, but let's take a look at this right here, and let's switch x and y, and let's resolve for y. times both sides by 2. And 2x plus 6 is going to equal the inverse of g of x. Okay, so now that we have the inverse of g of x and we have our original f of x function, it's saying, well, what happens if you have f of the inverse of g of x? So we know that we work from the inside out here, and we're going to take our inverse of g of x function and we're going to substitute that into wherever we have an x in our f of x function. All right, so we could say that this is going to equal something in which I don't have 2x plus 1 anymore, but I know that wherever there's an x, I can replace it with 2x plus 6. And if we expand and simplify that, you would come up with your solution. Okay, that's pretty much it for looking at inverse. Now there might be a couple questions that touch on reciprocals, and I know we don't look at reciprocals as much as maybe the book asks us to at times, but here's a couple examples that I just want to be able to give you just to branch out on that, and then we got a little bit of a summary finally at the end. So we talked about reciprocals last class, where if you have a function and you have y equals f of x as your random function, y equals 1 over f of x would become your reciprocal to that function. Okay, so think about what that means. If I take a random example, like y equals x plus 3, okay, and I say, well, that means that its reciprocal function is y equals 1 over x plus 3. And I know that this right here, if I put in the point, 4 right there, then I know that when I sub in 4 for x, I get 7 for y. And I know right here that for its reciprocal, if I put in a 4 for x, I would get the point 1 over 7. So when I keep my same x value, my y value gets reciprocaled. So the point xy becomes the point x 1 over y. So therefore, if you had a point like the point 28, its reciprocal would become 2 1 over 8. Okay, and then finally, an invariant point is when your point doesn't change after a transformation. So here's an example. We're going to be given something in which, well, here's a random function. Can you graph its reciprocal function? So whatever your y values are, based off of what we just saw, whatever your y values, you're going to take the reciprocal of that to find your new points. So step 1, sketch your asymptotes. Well, if right here, this is a y value of 0, and if I reflect that, or if I flip that around and I get something with 0 in the denominator, it now becomes undefined, and we represent that as an asymptote. So at no other point does it have an x value of 0, so that's going to be my only vertical asymptote. For the y values, I have a y value of 1 right here, and I have a y value of -1 right there. And that's important because when I take the reciprocal of 1 and when I take the reciprocal of -1, they don't change. So those points are going to stay exactly where they are, and they're examples of invariant points because y equals 1 or y equals -1. So they're going to ask us to fill in the rest. And if we have something here where you have, let's look right there, that's a height of 3. So the x value is 1, 2, 3, 4. So if this is the point 4, 3, we know that if we were to take its reciprocal value, it would become the point 4, 1 over 3. And we could continue to do that for some of our remaining points. and you're going to create something that looks like that. Now, think about why it goes up so much. If you take a point right here that just hovers above the x-axis, say it's at 0.1, it's at 1/10. If its y value right there is at 1/10 and you take its reciprocal, that 1/10 now becomes positive 10, and that's why it shoots up so high right there. The same thing's going to happen down at the bottom right here. And imagine right there, you have a point where your y value is something like negative 0.1 or negative 1/10, and you take the reciprocal of that, that becomes negative 10. So it's going to go down very quickly. And that would be what your reciprocal function would look like for that. And that would be an example of filling in the rest. Okay, final point right here before we get on to some homework. Take a look right here and see if you could pause this, and can you take the point negative 3, 4, and can you properly transform all of these graphs? So pause it right here, see what you get, and let's see if your solutions match up with what we have here. Okay, that's it for today. You can see the homework down there at the bottom. That's 2.4 and 2.5. Both of those are assigned right now. There's some good questions in there. Good luck, and we'll see you later.